So welcome everybody also from the Center Merci. It's my great pleasure to introduce Victoria to you and just say a few words and then we can get started. So as you already heard, she is an associate professor at the Department of Industrial and Systems Engineering at the University of Southern California. She has an impressive academic background, holding a PhD both in statistics and in law from Stanford University. She has had research stays at MIT and had positions at UC Berkeley, Columbia, and University of Illinois. And she is an international expert on improving the reliability of scientific results in computational research. She focuses on understanding the validity and reproducibility for statistical inference and the establishment of standards for openness and transparency in data and code sharing, what we'll see in her talk today. So we're really excited to have you. Victoria, you have been publishing more than 50 papers and 2 books. Besides the grants you're receiving here for your stay in Germany, you have also played a major role in all kinds of scientific advisory committees, kind of making your research come true and getting to life. So we are really excited about having you here. And let me hand over to you. Thank you.
Thank you, Melanie, and thank you, Dr. Roth, for the really wonderful and warm introduction and welcome. And also thank you, everybody, for being here. It's really such an honor. I'm absolutely delighted to be here, and it's such a pleasure to talk to you this afternoon. So I was thinking about what can I talk about in this lecture today, and what have I been thinking about? And I recently finished the semester at USC, and I had a number of interactions with PhD students. And one of the things that really was very notable is how excited people are about artificial intelligence and about deploying the tools of artificial intelligence in their work. And so this was something that I saw the students compelled with in accelerating all kinds of different facets of their research, and also just a general fascination coming from the students. So I started thinking about, what does that mean for the way that we do research? What does it mean for things like reproducibility or transparency, or even something as trivial that we all take for granted as understanding how those results arose? And I believe AI is going to have more than just an accelerating impact on the way that we do research. I believe it will be fully transformational, possibly even transforming how we think about a university and the role of the university in preparing and carrying out research. So the first thing I'd like to do is take a temperature reading of where we are. How did we get here, and what's going on in terms of the open research and the development of the ideas and the implementation of the ideas in open research? This, I'm going to try to argue to you, has led directly to breakthroughs and innovations in AI, the very ones that I mentioned my students were very excited about leveraging in their research and were actually already carrying out in their research. That lays the foundation for a discussion of how this changes or causes us to rethink our scientific norms. I'm going to try to convince you that there are fundamental changes at play here, and our traditional way of implementing our scientific norms is breaking. So where does that leave us? I think what we are headed towards is something I'm calling the digital scholarly record, and we will be producing different types of digital assets or digital pieces of scholarship, and I think these will start to come together into a digital scholarly record that I'll explain to you. Okay, so my background, I don't think I need to actually spend any time on this. Bill already did such a wonderful introduction. Just to let you know that I came from economics and the social sciences and then went into statistics and did my PhD in statistics on very high dimensional data. Okay, so open research in academia. This is something that has been almost an obsession in a way across society. And I think what we have been seeing and capitalizing on in academia is really a reflection of what's going on across all of society as we share data through, the most obvious example is through all of our social media tools, and We make open data almost just the way that we're starting to live our lives. What has been going on behind the scenes as we share with mobile phones and fairly large files of images and videos is an enormous infrastructure being built by mobile phone carriers, cloud infrastructure, data warehousing, and also the speed and the compression technology to be able to carry out our obsession with data sharing. This has trickled down to academic research. So many people probably have done things like work in Colab, right, or in Jupyter notebooks that are hosted in the cloud. And for some of the students, especially the younger students, this is a very normal way to work, and they probably wouldn't think of working any other way. Those breakthroughs, those technologies, my argument is this is coming from much of the advancement in our infrastructure through our mobile phone for the last 10, 15 years or so. Okay, so what has this meant to us? We've seen this meteoric rise in shared data, almost a cultural expectation of shared data now, and this wasn't how it was 10 years ago or 15 years ago. And also, I think lagging behind a little bit, but similarly rising, is this shared idea of shared code. Now, think about what you have been told in your classes. Some people probably still in classes, other people classes were a very long time ago. This wasn't something that was presented to you as the way that we do research. Somehow this has organically evolved, that we're now doing research more openly and sharing these parts of the research, and contrast that with our formal expectations of research, which of course is that published PDF, right? Very static object. So with all of this infrastructure development, we've seen institutional repositories coming up everywhere, science as a service, different platforms. I'm sure there's not a person in the room that's not using GitHub. Different data sets that are coming up from national funding agencies, and then these novel and I think highly impactful forms of finding results through things like Kaggle and Colab and other collaborative platforms that I'll talk about more. Okay, so what has this meant? The large language models that basically started getting attention about a year and a half ago are a direct result of the sharing of data. So I took this snippet from a paper that unfortunately the reference is cut off at the bottom, but that's the first Llama paper. And so this is a list of the data sets that Meta used to train its first Llama model. Okay, Crom and Crawl is research-oriented web crawling, books, for example, entirely open data. And you can see here that the idea of open data, if this didn't exist, we wouldn't have this one. This is Llama, but it's the same for OpenAI and for any of the LLMs. They're all riding piggyback on our obsession with open data that's been going on for many years. Okay, so what does this mean? It means that we're converting the output of our research from the PDF to now executable workflows, becoming a first-class object for researchers. Where does all this come from? So this is something that has been at least 50 years of grassroots efforts within academia. And the earliest work that I know, the references are a little bit cut off, but it comes from economics in 1986, talking about the need for open data, need for open code that connects the data to the results. And also in geophysics in around the same time, it may be more like 1990. And in that case, they're preserving their entire workflows to regenerate thesis results. And then it moved into signal processing and moved into statistics. And it's generally taken the form of the way that we typically do communication in academia when we have something to say beyond our research group. So these are National Academies reports or sort of institutional reports, policy changes that are happening at the level of the journal or the conference, and also efforts that come from societies and community standards like badging, for example, that has helped move the community together towards openness in code, openness in data, and towards reproducibility that's really driving a lot of this work. And in my experience, researchers are very quick to pick up tools that will advance their work. So what I saw in my class, the PhD students last semester, was the typical thing that you see. People are very hungry for their results and very eager to pick up new technological ways of getting there. So these are being embedded into our workflows already. Okay, very quick example of how this grassroots advocacy can work from within research. So this is back in 1986. There's a AAAS workshop on code and modeling and reproducibility. And I was one of the organizers of this workshop, and we put together a series of recommendations by gathering community members, talking about what the pain points were, and then putting these out as recommendations. And we had our publication, it's a little hard to see there, but our publication in Science. And essentially we focused on sharing these details, these digital details of the results that we've achieved and we're publishing, providing links to them so you don't read the paper a year later and can't get any of the underlying work, providing credit for this sharing, doing documentation, licensing the works correctly so that they can be used. Funding agencies can support this and pilot different ways to bring these standards and suggested changes into different research areas. And then maybe journals can start asking for reproducibility checks. So this was back in 2016 when we did this, and this is certainly not the only effort. And in fact, many similar efforts have happened in different areas and different fields going forward. You may have even been involved in some here. I think one of the most impactful steps that was taken is this 2019 National Academy's report, Reproducibility and Replicability in Science. Here it was a multi-month affair, many different people coming to meetings, presenting different ideas, many different themes that we explored. And we ended up similarly with the AAAS workshop, we ended up with a series of recommendations. The most important recommendation, I think, is the one where we define the term reproducibility and then we define the term replicability. And it's amazing how such a seemingly small step has really made a difference for people to be able to come around and coalesce on what these different terms mean. So here's what we said in the report. We said reproducibility, obtaining consistent results with the same data, same computational workflow, same code, same conditions of analysis. We could call it computational reproducibility, and that's what we mean when we say reproducibility. So this is the way that I'm using the term reproducibility in the talk today. It's around these computational components or these digital artifacts that are associated with the research. Before the report, people would interchangeably say replication when they meant computational reproducibility, reproducibility when they meant an independent re-implementation of the research. And so I think this is something that has really changed as a result of the report. So replicability, you have consistent results across different studies. So different studies that are answering the same question, are they getting roughly the same answer up to some error terms that are defined by the question? And this was extremely clarifying, I think, for the community, and just to disentangle the different discussions that were going on. My research has been focused on computational reproducibility, even though I get a lot of questions almost always, and maybe this is already in some of your minds. Why do we care so much about computational reproducibility? Isn't the real science and the learning in replication? Isn't that really what's important? I don't disagree with that. My standard answer for that question is, if you are going to understand how these different studies are producing the same or consistent results, or how they differ, we need to have a level of transparency in replicability that comes from computational reproducibility. So I think the first step would be that transparency in the computational steps underlying how the results were generated. Then we are able to understand why these different studies may be producing a similar result, or why different studies are producing different results. Seems to me that's the right order of operations. And also I thought it might be a little easier too. I don't know if it was that easy, but probably easier. Okay, so let's go back to AI. How does this idea of AI that I was talking about, these, for example, large language models, interact with these notions of reproducibility, replicability, these ideas that are our goals and our foundation for what we do in an academic setting? And why am I trying to tell you that it's disruptive? Okay, so let's think about the training. So I just kind of Googled around to try to understand at least some metric on how many resources or what types of resources were used to train various LLMs. And I came up with ChatGPT-4 trained on 20,000 GPUs for 3 months, and that was in 2022. Okay, another stat I stumbled across, and this was just basically Googling around. I don't know if these are particularly accurate, but they don't sound particularly wrong either. But Google's Gemini Pro trained on 40,000 TPUs, Gemini Ultra trained on 80,000 GPUs, apparently ongoing this year, 2024. I did find a Wall Street Journal article that said $50 billion were spent on GPUs in the AI industry, 2023. Okay, now let's think about if you wanted to train a model like this. Maybe some universities have some GPUs, right? There isn't a university that has the scale that's needed to train these models. And even if universities combine forces, we can't really play this game, right? We just don't have access to the scale and the compute resources. National Institutes for Health, I think their budget is something like $40 billion. National Science Foundation budget is close to $10 million, I think, last I checked. So there's 50 billion. So we take all of our National Institutes for Health, NSF funding, and maybe we're getting close to what was spent just on GPUs to train the LLMs in 2023. Okay, so right now and in any future, I can foresee this is not possible. Okay, so I keep mentioning how my students are very excited about using LLMs to leverage their research. So what are they doing? Of course, they're taking the trained models, right? And they're working with the trained models. Now, let's think about the reason for reproducibility. The reason for reproducibility is understanding how I went from data or whatever my input conditions were, and I figured something out, right? I made some meaningful contribution to science. I don't want to be told what the answer is, right? I want to understand why that's true. And that's always been how we've done science, right, from early days. Now, if I take a trained model that I had no role in training, and these sort of neural network-based models are entirely opaque. There's no possible interpretation, at least that I know of, that gives us something like interpreting a regression model or coefficients and so on. It's an absolute spaghetti. And so we don't interpret the models directly. We don't even train the models. And yet I'm trying to convince the community that somehow this output that's involved in my derivation of scientific results is trustable, is correct. So my big question, this is what has been on my mind for ever since LLMs appeared on the scene. How do we know this work is correct? Okay, I'm going to keep coming back to that question. Okay, so now we're leveraging AI and these digital assets in scientific research and discovery. So what does that mean? Okay, we have highly complex computation, data, integrated scientific workflows. The results of our research, our computational pipelines now, are not a regression model with beautifully interpretable coefficients that tell us how to change, you know, interest rates and what will happen to wages and so on. This world is long gone. Open, transparent, re-executable machine learning pipelines shared on common infrastructure. This is what people are doing. We have open data. And then the innovation that's happening in scientific discovery is deeply disruptive. The way of doing research that we're used to isn't the natural way when you are leveraging these machine learning pipelines to do your research. What people are tending to do, and probably people have seen or been exposed to this, my argument today is that this is becoming incredibly widespread and will probably eventually take over, is this what's called the Common Task Framework, a kind of Olympics of benchmarked competitions. So this isn't something that's coming organically from academic research. It's not how we were ever trained. It's more like a Kaggle style or Coda Lab style of doing work. As long as you have these agreed upon benchmarks, you compete to see who can do whatever it is best, right? According to whatever metrics are established. Okay, often this is leveraged by LLMs. And as I've discussed, the results of the LLM are opaque, not reproducible. Even if you have the model and you give it the same prompts in the same circumstances, you completely clear it, you have all the same parameter settings and so on, very likely you don't get the same output anyway. So in that sense, the result's not reproducible. I mean, remember, these LLMs being trained on their, tens of thousands of GPUs, TPUs, and so on in industry, they're not really created for solving scientific problems. If they were, transparency would be closer to the foreground. They're essentially an overlay on search. You think about why these tools were created by industry, what problems the different firms are trying to solve. It's generally not a scientific problem. But academia has a huge, long and very successful history of taking tools that are developed in other settings, like for example, in industry settings, and making them work, right? Excel is one of them. We have a long, that's an accounting software, and it's used all over scientific research. Okay, so we're in this setting where research is shared digitally, natively digitally, through GitHub, Kaggle, through other platforms and sources, or it's just not shared. Maybe it gets on archive. Publishing PDF, it's something maybe you'll do later if you have time. It's completely different. Okay, I'll give a little bit of a background on where these Olympic style approaches to research come from. And it goes back to 1986, but prior to 1986, there was a real effort around machine translation. So this would be happening in the 60s, late 60s, early 70s. And this is a much longer story, but the short version of the story is the results were not consistent from that program. They didn't seem to be making progress, and eventually they lost funding. There's a lot more to say about that, but that's essentially the crux of the story. And then time went on, 70s came and went, 80s came, and then there was a program officer at DARPA named Charles Wayne who had an idea that he thought could reinvigorate machine translation, and it did. The idea was define some objective evaluation metric, have a third party make an evaluation of the performance against that metric, and there's a holdout data set where that performance is evaluated by that third party. So in the case of machine translation in 1986, it was NIST, so federal agency, who had holdout data none of the machine translator had seen. And then they had to hit some target, send in your code, and NIST runs the code on the test data set. And then you sort of see who wins. So what this means is now we have open code. Right? These methods are revealed, at least they're revealed to NIST, or revealed to DARPA when they're shared, because they have to be run on that system. And the result was, before machine translation lost its funding in the late 60s, where it was accused of being full of mad inventors and untrustworthy engineers, peddling deceit and glamour, now we had organized benchmarks to ensure that we had clear, simple, sure knowledge. Okay. So this is really what's going on behind the scenes with Kaggle and with these Olympic style competitions. So what do we have in the Common Task Framework? A detailed evaluation plan developed in concert with the community. Automatic evaluation software, in this case, written and maintained by NIST, published at the start of the project, so everyone knows what they're going to have to do. And then shared data. So you get your training data, test data is withheld, periodic evaluations, community can decide on the details, but the first Kaggle, in a sense. Okay, machine translation took off, right? Everyone has the results on their phone. That's the program that produced Siri, for example. Okay, so here's a thought experiment. Let's suppose in some not too distant future, LLMs are routinely leveraged for things like metadata completion on data sets, the headache tasks no one wants to do, but we should do it. Now, because of that, data sets are more easily integrated. They are more easily accessible. This idea of benchmarking, of clear and concise solutions and providing definitions for what a solution actually is, has been standardized across research. We know how to do the benchmarking when we're doing our work. AIs are out there crawling pipelines to find the best solutions in a sense. They're just sort of doing these applications of these first-class objects, these digital workflows, and applying it to open data, standardized benchmarks, and I think you see where it's going. How do we choose the problems to actually work on? I'm also very interested in that question. I don't know if LLMs can help us or not. I think one of the hardest things about being an academic is choosing the right problem to work on, and there's some deep level of creativity and understanding in that task. Will they get there? I don't know. Maybe. No, I don't know. And I think in a shift to this research paradigm, we will have winners and losers, not just in terms of the research questions that are being asked and answered, but think about the type of work that you would need to do to engage in one of these sort of research Olympiads versus the type of work maybe that you do now. And it's a different type of engagement with the community. I don't know if I would like to sit there and write my books. I don't know if I want to really compete down to like margins of error of like 0.5% or less or whatnot to try to see who can win and so on. There are some people who are very motivated by that type of structure. And so maybe academia starts to shift to favor those people and people who have access to the resources to be able to do that, engage in these types of competitions. So to me, like equity is something that comes up immediately as soon as I start thinking about what this future might actually look like. Okay, so there are all these problems, but fundamentally, I do want to know that whatever the winning solution is correct in some sense. And I'm struggling with the lack of transparency in the idea of reproducibility, which, by the way, has been left behind. My whole entire research agenda has been left behind by this paradigm change. We're not looking at the code. We're not understanding how the models work. We have black boxes, we have some inputs, and we get some outputs. So this means that what we need to do is become specialists in probing these black boxes and understanding what tests or what questions to ask to understand how these workflows actually work, whether or not this is correct. And we need to be, in my opinion, a lot more careful in understanding the input data as well. But that's my best guess at how we can get a handle on judging whether this output is correct or believable or trustable or not. Okay, so this I think is going to make, and is already making, a disruption in scientific norms. Okay, so we're in the future. Let's go right back into the past when science as we know it to some degree was canonized. That was around 1660. So this is a photo of Robert Boyle. You recognized him. He was one of the founders of the Royal Society of London, the Invisible College. The picture on the top right there is the first journal. So these sort of learned gentlemen, and of course in those days this was all men, getting together. They discussed their ideas, and these were scientific ideas around understanding the vacuum, for example, and other questions they were asking. Sent furious letters back and forth. I don't know if they were furious. Sent many letters back and forth, trying to understand and explain their ideas. This became frustrating to the secretary of the Invisible College, who just ended up effectively stapling them together, calling it a journal, and that was our first journal. So you can see it here. It's a little hard to read. Philosophical transactions, giving some accomplishments of the present undertakings, studies, and labors of the ingenious in many considerable parts of the world. Okay. So they were modest, we knew that. Okay, so this is where we started, and Boyle was the one who actually set this idea of reproducibility into motion and into part of what we understand as a core part of a scientific result. So he wrote this book in 1660, the new experiments, physico-mechanical, touching the spring of the air and its effects. And in this book, he said, if you're going to publish in this new journal, you need to have enough detail on your equipment, your materials, your procedures for reproducibility. There's another long story here. He couldn't reproduce a Dutch researcher's vacuum pump. And so he started putting all these standards in. And that was one of them. Another one is communal witnessing. So if you're creating a vacuum or whatever your discovery is, have people around who can witness this. And then include exhaustive details on experimental settings, false starts, failures, and so on and so on. Okay, so they're not too far from the standards that we have today. We've evolved them a little bit, but it's not too far. He also has another beautiful quote. It is much more difficult than most men can imagine to make an accurate experiment. Okay. This is 1673, so about 13 years later, in his tract, Certain Physiological Essays and Other Tracts, written at distant times and on several occasions by the Honorable Robert Boyle. Okay, so what has happened? 1660s, this is where we started. That was our sort of draft one of what it means to produce a scientific result. Around 1900s, we formalized these journal publication standards into something everyone recognizes today. You have an introduction, introduction, method section, results, discussion, and this is what's required for their scientific publication. Okay, what's happening this year and in the future? I believe we go through this phase transition. We are sharing our executable workflows. It's completely different. It's not a journal paper anymore for the first time since 1660. These are executable objects, these workflows. They have links to their corresponding data, and they have links to their results. They're openly accessible. Okay, so what's the impact? The first change is, what on earth does authorship mean in this new world? In Boyle's day, think about communal witnessing, right? Authorship, who did it, who did what, it's very important. Our demands around citation are all about authorship and about giving credit for discoveries that were made or contributions that were made by certain people. Leveraging LLMs, other large language models, this breaks this chain of authorship, or even breaks the notion of authorship. Who is the author? So let's suppose part of your proof, you relied on an LLM. Is it really your work? It certainly didn't come out of your mind the way we think about publishable works, but you did use the LLM, or maybe the LLM should be credited. Suppose I want to build on your work that has that part of that proof that came from the LLM. How do I give credit? how do I know which ideas I'm really drawing on and what's important when I'm advancing the scientific threshold? These are fundamental questions we have answers to today. And our reliance on the LLMs is upending all of this. It's upending our idea of authorship. So is the reasoning human accessible? So if I have, presumably if I have a contribution from an LLM and a proof, I'm still reasoning through that proof. It's not the case for all LLM output. We may have LLM contributions that are entirely black boxes, similar to the sort of Kaggle Olympic style competition. So then what do we do? The whole reason for science is for human understanding. Now we're entering this world where that chain of reasoning and the result that we have is not human understandable. And we have no chance, short of more sophisticated queries on this pipeline, other things we might be able to do, but organically understanding the logic, no. Okay, second thing. Knowledge becomes something of a utility, not something that we associate with understanding. So results are believed correct because we trust the process that delivered them to us. We don't independently think through or verify them in some way that we're used to doing today. Okay, so this makes me think that our task needs to be for trustable, verifiable truth around the world, some semblance of truth, what we've been going for with scientific discovery all these hundreds of years. We need to rethink and develop our scientific method for that common task framework, the challenge framework that we're headed towards. So things like whether the quantitative goal of the challenge problem will support scientific conclusions, questions we were never trained to ask. What does it mean to have a meaningful and precise description of the problem? What qualifies or what doesn't qualify? What's a good benchmark and what's a terrible benchmark? That seems fundamental to the reliability of the output. Is the data appropriate? Is the data representative of the population that we're looking to investigate? How has the sampling been done? What other problems might be in the data? Suddenly, we've asked these questions about data ever since we started working with data, but now suddenly they're highlighted. And again, what problems can we best solve with this approach? And what are we looking for in our data? What are the attributes in the data that allow us to apply this method? And have some level of trust or confidence in the correctness of the results, whatever's coming out of that black box pipeline. Okay, so for the data, measuring how well the data span the true underlying population of interest that I just mentioned, measuring sample representativeness. So we have ways, these are not new questions, and they come in every time we have data that's applied to a problem, but it's not always our focus to think about what are the appropriate metrics of representativeness when we have our sample. Was our test set sampled from input data? Is it a new sample? If it's a new sample, likely that's higher variability. So how do we start thinking about things like confidence intervals or standard errors on these results? I'm very interested in the statistical output, sort of inferential output from these computational pipelines, and whether we're really understanding how much variability is injected into those results just from the computational implementation alone, not from the mathematics and not from the model. It's already in there, but we must be adding more with the computational implementation. Taking out of sample test sets must be adding more variability that we need to account. We'll be overly optimistic in our results otherwise. Okay, so where is this getting us? Convergence, all of this I think comes together. It's pieces of this digital scholarly record. Okay, so what do I mean by that? I'm thinking about a verifiable, extensible database that's been collected systematically and in an open way. And what can we do with this? Okay, this is all the little bits and pieces coming together. These shared workflows, the open data, results lying out there. Remember, they're linked for certain scientific inference. Okay, what are we going to do? We're going to knit them together. They're going to get knit together. And they're going to allow us to do things like regenerate results, regenerate models, compare and reconcile inferences around various hypotheses, right? So it's almost like a question. As soon as I pose it to you, if you haven't thought of it already, you're going to be like, of course, this is obvious. Our current scholarly record, why can't I automatically query all the work that goes to a particular scientific question or a particular hypothesis? It seems like what I want to do. And then it's only, if you have these open executable workflows, it's almost trivial to have some human or bot crawling to understand why they're different. Like maybe this rejected the hypothesis for this reason and this didn't for that reason, and settings are different, or at least start to understand the contours of when those inferences apply. This would be possible. Re-implementing methods on new data, updating of methods. So in this fabric, this digital scholarly method that I'm thinking of, let's suppose some new data is linked to a workflow or linked to results. Why can't I apply other workflows with that data now? Or if there are workflows that could be applied to already existing data and so on, we can start to kind of, and think about those AIs, the LLMs, who are going around creating metadata and making data more interoperable or more discoverable and so on just while we were sleeping. So that's when it starts to pay off. Now the data starts to become accessible and integrated. We can generate and we can evolve benchmarks, standardized test beds, and we'll do a better job with assessments of models and inference methods. And because this is some collection of digital detritus in some sense, we can start thinking about governing policies. So things like data privacy, ethics, meta research on the scholarly record, because it's queryable. How many researchers in Germany investigated this question and got results last year? Something like that. Just not a query we can do now in the scholarly record, but maybe it will be interesting. Okay, so we'll end up with a digital scholarly record. It's also useful for the robots. So now we're fast forwarding to 2050. In scholarly record, we collect these organically connected frameworks, training data, leaderboard results, these executable workflows. Correctness is not established by transparency, human verification, replication, the way that we do it now, but by direct checks in a new meta-Bacon methodology. Okay, so in the interest of time, I took out a slide where I talked about the contributions of the various men named Bacon to the development of the scientific method. What I mean here is extrapolation. So what we can do is we can verify conclusions by direct experiments on the black boxes. So what happens when I query or push the LLM in some way? Can I actually understand how the results change? Discovery of truths unreachable by other approaches. So that's directly from Bacon, in that we're going to be able to extrapolate. Investigation of the secrets of black box discovery methods, and that allows us to have a greater knowledge of past and future. Okay, so we will not be touching Boyle's spring in the air, but what we do is we generate a collection of useful results that work. And I think this may be the future where we are going. Okay, so that the chain of logic behind the discoveries is accessible to the LLMs. It's impenetrable code to us. However, with this idea of a digital scholarly record, I think tools will develop and will be much more sophisticated at querying and understanding what is happening in the generation of the results. This will be open and it will be essentially executable. Okay, so is this all bad? Depressing? I don't know. No. Okay, so a digital scholarly record, it will still act like a traditional scholarly record. So it's still a place where the community comes together to share ideas. So you know where to find other people's ideas on certain topics, get feedback, improve the work, agree on priorities, resolve debates, all these things. This is the function of our, or part of the function of our current scholarly record. Integrating AI allows us to document and trace contributions in some version of authorship, expose pipelines, have automated testing, discovery verification through replication. I could imagine bots just kind of rerunning results to check them or update them as software changes. Okay, so what will we have? A queryable, extensible open knowledge base that synthesizes computational and data-enabled discoveries. It gives us reusable discovery pipelines, regeneration of results, reimplementation of methods on new data, comparisons, reconciliations of the different conclusions we might get from the questions, generation and evolution of benchmarks, standardized test beds, all of these things that are foundational to understand when we're making progress and when we're not. Development and application of the policies regarding data privacy, ethics, and so on, and maybe even in an automated way. Okay, so where does that leave us? We don't know how we got these results. And in this great rush to Olympic-style science, nobody seems to care. Models containing billions of parameters, certainly not understanding how those predictions are made. Focus on producing results that are attuned to the benchmarks rather than some explanation of what's going on in the real world. We've always had this assumption in science that our minds could understand science, the sort of reality. So what's going to happen is we lose, or at least this is what I think could happen. We lose this idea of peer review as a pillar that allows us to trust the output. Okay, what journal it's in, how it's been reviewed is something that we all rely on extensively. We lose this disclosure of methods that humans would find transparent. And then our trust in the results is not bolstered by independent reproduction of the findings. So what that means is what we trust is the process, right? So the guardrails in the process become even more important. The general stakeholders we think about in academic research, funders, researchers, publishers, scientific society, regulated bodies, institutions, libraries, all play a role. They've played a big role in bringing us to the open data, open code, the transparency in the scholarship that we have emerging now. And I think they're also important in shepherding the development of a digital scholarly record that is in the interest of the science. It does continue to engage our research. Okay, so I'm almost at the end of the talk. I did want to mention the workshop tomorrow that I'm doing with students. And what I would like to do in that workshop is take some of these ideas and look at it in a very concrete setting of particular research problems in particular settings and particular environments. And so this is what we're going to do tomorrow. Okay, so just to wrap up, my main point is challenge problems. I think they're taking a much larger and larger foothold. We will be headed towards a future of opaque models rather than ones where models are some explanatory force for natural phenomenon. We're leveraging AI, which threatens our traditional notions of authorship and accountability, this idea of understanding, whatever that may mean, and then promotes an emergent digital scholarly record. So our task is, how do we develop a scientific method producing correct, trustable, reliable results for AI-enabled research? So I went to, this picture is here, I went to ChatGPT-4 when I first gave a version of this talk last year, and I asked it to draw a robot touching the spring in the air. This is what it gave me. And then it said, here's a surrealist style drawing of a robot touching a spring in the air. And so this is maybe our new Robert Boyle.
So let me thank you for a great and very thought-provoking talk and for a very interesting discussion. So.